In the 1920s, everything we thought we knew about the universe changed. Astronomers looked up into the night sky and realized that the galaxies and other bodies appeared to be moving away from us. There seemed to be only one reasonable explanation. They had discovered evidence that the universe was expanding. This is a pretty mind-bending concept, but there's an easy way to imagine it.
Okay, so bear with this. The stars on this balloon represent galaxies, and the black balloon itself represents the fabric of space-time. Okay, one more. So let's say that this star here is us, and then we've got this galaxy nice and close, which is about 2 centimeters away, and then we've got another one over here, which is 4 centimeters away. So what I'm going to show you now is the universe expanding in real time. By my measurements, this has just doubled in size. And in that time, this galaxy's gone from 2 centimeters away to 4, but this one's gone from 4 centimeters away to 8. So it appears from where we're measuring that the further away galaxy has moved away faster. Now, the analogy's not perfect. I mean, for one, it looks like the stars are stretching, but the galaxies aren't actually growing themselves. Also, it kind of looks like everything is expanding from a central point, which isn't real in the actual universe. However, it really shows that idea that the fabric of space-time and therefore the universe is stretching.
And a deeper understanding of this expanding universe could be just around the corner.
Welcome to the Sky at Night.
When Edwin Hubble discovered the universe was expanding around 100 years ago, the foundations of astrophysics were changed forever. It suggested the universe started as one point in time and space and underpinned the theory of the Big Bang. But understanding that it is expanding was just the beginning. What followed was the challenge of getting an accurate measurement of how fast. Ever since then, we've been trying to pinpoint that rate of expansion. With each new generation, we get closer. But we're not there yet. Right now, in the UK, astrophysicists are working on 2 brand new telescopes. And with these telescopes, we hope to find the answers. It's only by understanding our expanding universe that we can unlock some of the biggest questions, like the size, age, and even ultimately the fate of our universe. Chris is at Radcliffe Observatory in Oxford to look back in time.
It's still astonishing to me that we don't just have to imagine the start of the universe, we can actually see it. It's like a paleontologist watching a T-Rex with binoculars. By looking at ancient light called the cosmic microwave background, or CMB, and comparing it to what we see around us in the present-day universe, cosmologists like David Alonso can work out just how fast the universe is expanding today. So David, what is the cosmic microwave background?
Well, so the cosmic microwave background is essentially the first light that reaches us from the beginning of the universe, right? Because if it's expanding today, it must have been a lot more contracted in the past. So that means that all particles that made up the universe, they would be interacting with each other very, very often.
The early universe was a dense soup of particles, thick enough that light couldn't move freely. As the cosmos expanded and cooled, it became transparent, letting light travel across space. And it's light from this time that we see as the CMB, with tiny variations, these blobs on the map giving us a glimpse of the early universe. So how can we use the CMB to measure the expansion of the universe?
So if you imagine that this is the size of one of these blobs, right, given by this ruler here, And if I put this ruler very close to me, I will have to look like this in order to see the two ends of it, right? Because it spans a very large angular size, right? If I bring it further away from me, then it looks smaller, right? You can grab it, yeah.
So as it goes this way,
exactly,
it gets smaller.
It gets smaller, it does like this, right?
It forms a smaller and smaller angle as you measure it.
Exactly. And so if we know exactly the size of the ruler and we measure the angle, then we can know how far away from us it is. And so if I do the same thing with the blobs of the CMB, what this tells us is what is the distance that the photons of the CMB have had to travel since they were emitted.
Satellites like Planck have scanned the skies, capturing the ancient light left over from the Big Bang, producing wonderful maps of the CMB from space, like this one, released in 2013. And by starting here and winding forward to our present-day universe, scientists are able to estimate how fast the universe must be expanding right now. But a new ground-based observatory is about to provide the sharpest images of the CMB yet, revolutionizing cosmology forever.
The new experiment that I'm involved in is something called the Simons Observatory. The Simons Observatory is this set of telescopes put in the Atacama Desert in Chile. And so it's a new observatory made out of 7 telescopes. There's one telescope called the Large Aperture Telescope, which is a huge 6-meter telescope that will measure the CMB at really, really high resolution. And then there's the small aperture telescopes. There's 6 of them. We call them the SATs. And the main goal for those telescopes is to measure the polarization of the CMB at large angular scales, because that tells us something about other properties of CMB that we're interested in, which could tell us about the very early universe.
It's possible that these new, sharper images of the CMB will confirm the calculations of the current speed of the expansion of the universe. Now, while the ancient light of the CMB can be used to calculate that speed, other methods use light from exploding stars or supernovae in the present-day universe. And these 2 ways of measuring the speed the universe is expanding, well, they don't match, and that's a problem.
It's interesting that we get measurements of this expansion rate that are really, really similar, but not exactly the same.
Do you think that's just a mistake somewhere? Do you think that's new physics? Like, what will happen in the next, say, 10 years on that?
In terms of the CMB, there's been measurements of the expansion rate from experiments that have come in between Planck and us, and they all seem to agree. I think it'll be great when we do this with Simons Observatory. We'll be able to get a completely independent measurement of it. So we will know actually whether it's real or not. I don't want to say whether it's real or not, because I don't know. If it turns out that it increases in significance, the level to which these 2 numbers are different, it will be really exciting, because that is then definitely telling us that there's some new physics, either in the very early universe or in the very late universe, that we don't understand, and then we need to figure out what it is.
So how are things going? I know Simons is just getting started,
yeah.
But when can we come and talk to you about results? When will you have cosmological results, do you think?
In principle, Simons Observatory is going to be observing for 5 years, and we will be putting out results every year or so. But in between getting the data and being able to say this is the number for expansion rate, for example, there's a lot of work that needs to happen and a lot of making sure. So sometimes that gets delayed. I would say 2 years from now, maybe come to me, we'll have the first results.
It's intriguing that this measurement of how fast the universe is expanding made with this CMB doesn't agree with the result you get if you use local stars or supernovae, things that surround us in the universe today. And that difference is one of the hottest topics in modern cosmology. Now, it might be that we just don't understand supernovae well enough. It might be that there's something we're missing about the CMB, about the early universe. But there's also the possibility that something's really wrong with our cosmology, that this difference is telling us that there's something we don't understand, that there's a novel force or some new effect that we've never thought about. Is that true? We don't know, but the Simons Observatory may well tell us. While we wait for the new CMB observations of the oldest light to see if it can help determine the exact speed the universe is expanding today, it's new strides in the study of more recent phenomena that may help solve another cosmological conundrum, one that came about from studying supernovae.
Because these supernovae were so distant, they gave us a glimpse of our cosmological past and a way to trace how rapidly the universe had expanded through time. And they made an astounding discovery. The expansion of the universe wasn't slowing down. It was actually speeding up. This was a real surprise. If anything, gravity should be slowing the expansion down, like dust and debris settling after an explosion. Ever since, we have made huge strides in calculating that rate of expansion. And when we pin it down, it will reveal how our universe has changed in the past. But more importantly, it will show us how it will change in the future. Phil Wiseman specializes in studying supernovae and this accelerated expansion of the universe. Now, you use stars to understand the expansion of the universe, but can you tell us how that works?
Yes, so a particular type of star called a white dwarf, it's actually a small old dead star. If it's near another star, it can actually gain material from that star. And once it reaches a certain mass, it will explode. Explode as a supernova.
Supernova, lovely.
And because it always is exploding around that same mass limit, it's almost always the same brightness. And that's actually really helpful for us. I've got a little demonstration that I can use to help explain this.
I love a demonstration.
So this little light bulb, we're going to pretend is a star about to explode.
Yes.
And when it does explode, it will light up. But before we light it up, if we could turn the lights down.
Magic.
Pretending we're now in the universe. So the star now explodes.
Okay, so it's gone supernova.
And just like the light bulb, we know how bright it is.
So all type 1a supernovas have more or less the same brightness?
Exactly that.
Ah, okay.
So if I take this star, pretend we now have a new star that we explode from here, this should now seem fainter for you.
It does, but I guess it's the same intrinsic brightness because it's the same light bulb or the same type of star.
Exactly. So you'd be able to measure the distance to this light bulb by how faint it now looks to you.
Yes, yes.
And what we'll do is take it one step further, explode one in the distant universe. And so now you can measure more distances. You can measure distances further out in the universe and therefore actually further back in time. I'll bring you the supernova back.
Yes. Astronomers then combine the measured redshift of the supernova's host galaxy with this distance. Redshift is what happens when light from an object gets stretched into longer, redder wavelengths as it travels through the expanding universe. The further a galaxy has been retreating, the more its light is redshifted. This tells astronomers how fast the host galaxy of the supernova is moving away from us. This combined data gives us a snapshot of the speed of expansion over time. So we've been using these, but there's a new kid on the block, a new telescope, Vera Rubin. Can you tell us how that's going to actually improve the observations of these type 1a?
The Vera Rubin Observatory, which is now already starting to observe the sky in Chile, is probably and arguably the most amazing, most technologically advanced telescope that we've ever built. But the real centerpiece is the detector, what actually detects the light from the universe. That's by far the largest digital camera that has ever been built, 3.2 gigapixels.
The charge-coupled device, the CCD, that is the detector.
Yes.
And we have them in our mobile phones, but on a much smaller scale.
Exactly, exactly. So this CCD is actually so sensitive that if you were stood in London and someone had a candle in Honolulu, then Rubin would be able to see that candle.
Yow. Okay, that's impressive. So you're observing supernova at the moment, but how is Rubin's going to be a game changer?
To put this in terms of pure numbers, so far over the history of astronomy, we've found somewhere between 20, 30,000 and 100,000 supernovae. Rubin will find 1 million a year.
Whoa. Okay. So brace yourself for the data. It's coming through.
It's just...
So with the onset of Vera Rubin, it's going to be incredibly exciting, all these supernovas coming through. But how will that help us refine the expansion rate of the universe?
By putting 10 times more supernovae on that graph than have ever been on before, drawing a line, which is the expansion rate, becomes much easier.
Ah, yes.
The other great point with Rubin is that most of these supernovae will be further back in time, further away than where most of the supernovae we've got before are. So that gives you a better lever arm to compare the expansion rate now to the expansion rate back in history.
Yeah, and I suppose it's the gradient of that curve that really gives us the understanding. And so having more data points up here will fix it better. Wow. Getting a better understanding of this changing expansion rate could give us a better understanding of how our universe has been changing in the past. But it could also tell us about our future. If you were a gambling man, what do you think? Is the universe going to continue expanding? Is it going to contract?
I'm really having to sit on the fence with this one. We've made some tentative breakthroughs in the last couple of years that would suggest that it might not be the expanding on forever universe that we've thought it has been for the last 25 years.
Right.
Rubin will put this to bed,
Yes.
But I'm going to sit on the fence until
More
it does.
data needed. Isn't that always the way?
Yeah.
As astrophysicists work ever harder to measure the universe's expansion over time, what's causing that acceleration still remains a mystery.
When it was first discovered that the expansion of the universe was speeding up and not slowing down, the term dark energy was coined to represent what might be causing the acceleration.
Dark energy isn't something we've seen or even remotely understand. It's just sort of like a nickname. It could have just as easily have been called invisible power or even dark force.
We can't detect it directly. We have to learn about it by observing how it shapes our universe's matter and speeds up its expansion. Seshna Datta is working on probing the effects dark energy has on our universe's cosmic structure.
So you work with dark energy, and I'm going to start you off with a big question. What is the evidence for dark energy?
All the evidence that we have for dark energy really comes from us measuring distances in the universe and how fast the universe has been expanding with time. And the evidence showed in 1998 that the expansion had been getting faster with time, so it was accelerating. And we don't know what's causing that acceleration, but whatever it is, we call it dark energy.
But I guess we can't really investigate dark energy directly. We're looking at the effects, right?
Exactly, that's right.
So how are astronomers tackling this right now then?
Well, one of the things that we're doing with a big survey collaboration called the Dark Energy Spectroscopic Instrument, or DESI, that's what I work on, is we're building a giant 3D map of millions of galaxies. We've got up to 30 million now, but we're aiming for over 50 million. And looking at the patterns in that map in order to measure distances even more precisely, and therefore work out how the universe has been expanding going back over the last 11 billion years. And we use those distances to determine how fast the universe has been expanding with time to great precision. And that allows us to measure what's been happening with dark energy.
And you say you've done 30 million of them already so far.
Yeah.
Wild. Okay, so how is this map then, this 3D map, helping us to measure the speed of the expansion of the universe?
So there's a very cool feature that we can extract once we've got a map that's big enough, which is actually a leftover little pattern, like a ripple, that comes from the very early universe and just got frozen in time at this early time. And now you can still see it in the distribution of galaxies today.
Just after the Big Bang, before the CMB was emitted, the universe was a hot plasma of particles and light. In this plasma, pressure waves or sound waves rippled outward through the early universe. These ripples, called baryon acoustic oscillations, or BAOs, left a faint imprint on the distribution of matter. When the universe cooled enough for atoms to form, these ripples were frozen into the large-scale structure of the universe.
The cool thing about this pattern is it serves as like a little scale on our map. Once we see it, we know how far away those individual pairs of galaxies are, so we can work out how far away they must be from us today, and we can use that to measure distances to galaxies at various points in our map.
11 billion years are then already mapped out. That's quite a lot already.
This is impressive work, but when combined with the data from the ancient CMB light and more recent supernovae, things get even more exciting.
We can actually combine our measurements of these ripples, the BAO feature, with other data to extend that read. So, for instance, we get data from the cosmic microwave background, or the CMB, which is even earlier, further back in time, and also with the supernovae explosions, which help us map out more precisely the very, very local universe that is very close to us. And by putting all of these three together, we can span an even wider range of time and distance.
Okay, so that's very impressive. But of course, now I need to ask, what are the results?
Yeah, well, the results have been very exciting because what we found is that the rate at which the universe appears to have been expanding over this time does not match our simplest model of what we thought dark energy was, which is what we've been working with for the last 25 years.
Okay.
And in that model, dark energy was a cosmological constant, which means that it was the same over all time and space. But now it appears to be contradicted by this new data, which seems to show that it has been changing with time.
If this is confirmed, the changing behavior of dark energy over time could not only give us a better understanding of what dark energy itself is, but it also might solve cosmology's other problems.
We seem to be kind of like on the precipice of, rewriting the physics books. Our understanding of the universe is just fundamentally changing. How was this for you, kind of discovering this and seeing this for the first time?
Well, I've spent the last 15 years just thinking that dark energy was going to be a cosmological constant, and we just measure it better and better. So this has been a real surprise. In fact, at the time when we first saw our results, one of my colleagues sent me a picture of our results with no comment and just an emoji of an exploding head. And that basically sums up our reaction to it. It's new, it's very exciting, but we don't quite know what to make of it yet.
I like that. It's kind of classic academic, sort of like, just an emoji for like, physics is different now. We are constantly testing and measuring the universe around us because the truth is we only know and understand a tiny portion of how the universe actually works. So DESI, along with the Vera Rubin Observatory and the Simons Observatory, will all be needed together if we're going to finally unravel the mystery of what is accelerating the expansion of the universe.
While we scratch our heads over the mysteries of the expanding universe, it's time to stop and look up to see what wonders to look out for in the coming weeks. Pete is at South Herts Astronomical Society to tell us more.
This month brings us the Northern Hemisphere's autumn equinox, a time when the length of day and night are more or less the same. That occurs on the 22nd of September. Now, the nearest full moon to this equinox is defined as the harvest moon, so called because it's said its light helps farmers gather their crops. In astronomical terms, the difference between moonrise for the fuller phases of the moon over consecutive days is at a minimum at this time of year.
On average in the UK, the difference between moonrise times from one day to the next is around 50 minutes. But around the equinox, it's typically less than 15 minutes. To locate the rising moon, just look east-northeast in the early evening. On the 6th of October, the full moon rises at 18:14 BST. The next day, on the 7th of October, moonrise is at 18:25 BST. And on the 8th of October, moonrise is at 18:40 BST. That's an average difference of 13 minutes.
Earth isn't the only place to have equinoxes. All of the planets have them, and they make for some interesting viewing. Let's take Saturn, for example. This had an equinox back in May of this year, when Saturn was effectively sideways onto the Sun, and the Sun was on Saturn's equatorial plane. This resulted in the rings appearing very narrow and thin, and Saturn's largest moon, Titan, being able to pass across the planet's globe, behind the planet's globe, and also into Saturn's shadow. From Earth's perspective, we saw Saturn go edge-on back in March of this year, and at that time the rings virtually disappeared from view. However, at the time, Saturn was too close to the Sun to be seen, and after that the rings began to open up again. But the jostling positions between Earth and Saturn means that we get to see the rings go virtually edge-on again between mid-November and mid-December. And it's after that that they start to open up properly once again.
Saturn is currently in a good position for observing, reaching opposition on the 21st of September. Around this date, it can be found due south around 1 AM BST, roughly 1/3 of the way up the sky. It's near two asterisms, or unofficial patterns, known as the circlet and the water jar. There's a special Titan transit occurring in the early hours of the 20th of September as dawn is brightening, when the moon and its shadow cross the planet's globe in sync. Such a sight is very rare. Titan's shadow transits will end in October, meaning you'll have to wait approximately 13 years for them to start up again.
Jupiter is also coming back into view, and it too is heading for an equinox in December of 2026. This is currently providing some great opportunities to see interactions between Jupiter and its outer Galilean moon, Callisto.
Jupiter can be seen climbing high above the southeast horizon in the run-up to dawn. It's the brightest thing in the sky apart from the moon when it's around, and if you wait long enough, Venus appears low in the east as dawn is breaking. Using a telescope, it's possible to see Callisto's shadow pass across Jupiter's disk on the 15th of September between 0210 and 0500 BST.
As ever, if you do take some great images of the skies, do share them on our Flickr account. And you can find details of this and my full sky guide at www.bbc.co.uk/sky at night. Meanwhile, here are some of our recent favourite submissions.
Sort of get used to the idea of a big bang and an expanding universe, but it's intriguing to hear that we don't understand the details of this expansion, that there might be new physics lurking there waiting to be understood. I'm excited by these new telescopes that will help us solve these mysteries and tell us new things about the cosmos. And speaking of mysteries, remember to send in your space mysteries for our show coming up with the hit Radio 4 programme, Curious Cases. If you have a question the team could investigate, submit it now to curiouscases@bbc.co.uk. Good night.
Uncover the mysteries of stars, space and distant planets with a special collection on BBC iPlayer, Exploring the Cosmos.